Okay, so maybe let's start the session before lunch. So our first speaker is Samir Khuller. He will be talking about an optimal local algorithm for connected dominating sets.
Thank you so much, and thank you, Ali, and the organizers for inviting me to speak. I was pretty excited. A workshop on local algorithms. I guess I'm a local speaker, so that makes total sense. But also, some of this work actually goes back almost 3 decades, and it's sort of interesting that every time I go back and spend some time studying this problem, I learn something new. And it sort of reminds me of how I used to cook when I was in grad school and how I cook now. And when I was in grad school, I had very limited amount of time to devote to cooking. Okay? I guess I have limited amount of time even now, but I invest more time in it all the same. And so, for example, I could never convince my family members to eat tofu. They always preferred paneer. But finally, I figured out how to make tofu so that it tastes like paneer. So again, these things, you cook the same dishes again and again, but then someday you learn something new. So this problem like that is like that for me. Every time I've spent some time thinking about it, I've learned something new. Okay? So let me start off by just reminding everybody about set cover and capacitor set cover, because the story sort of begins then. So capacitor set cover is a generalization of classical set cover. So you have a bunch of elements, and then these elements are belonging to some subsets. And you can buy subsets in standard set cover by paying some price. And the goal is to pay the smallest amount of money to buy sets to cover all of the elements. In capacitor set cover, when you buy the set might have 15 elements in it. But if it has a capacity of 5, then you can only cover 5 of those 15 elements. And you get to decide which subset of the 5 elements you want to cover. Okay? So again, the same kind of greedy algorithm that works for set cover also works for capacitor set cover. But there's many more applications of capacitor set cover. Set cover also has many applications. So there was work on influence in social networks, detecting disease outbreak. But the most fun place where I came across this is a SODA 1997 paper on the Sloan Digital Sky Survey project. So here, in this project, they're trying to minimize the number of placements of a telescope. And once they choose the position of a telescope, then even though the telescope is pointing at, say, 600 stars, there's some inherent capacity. So maybe it can take readings from 100 of those 600 stars, and you get to decide. There's a lot of geometry in that problem that they also exploit to solve this problem. And it's more about not proving approximation guarantees, but utilizing techniques from approximation algorithms with developing practical algorithms. Again, classical greedy set cover, many of you know, goes back to David Johnson's initial work, where he at least looked at the unweighted set cover problem, where he just said, just keep picking the set that covers the largest number of uncovered elements at every step, and this gives you like a log approximation. This then was extended to the case by Lovash and Schwadal independently for when the sets have cost, and then Woolsey finally showed a very general framework capturing submodular functions, where at each step you pick the set that gives you the maximum incremental benefit, and that has to be computed carefully when sets have capacity, but fundamentally they all give you a log of the largest set size approximation bound. And the idea behind this bound is somehow you have a greedy algorithm running very nicely, and how do you analyze these algorithms, because you don't know what the optimum solution is. So in this trivial example, optimum solution has only 2 sets, the 2 horizontal ones. But the greedy algorithm running might not find the optimum solution. So for example, each optimum solution has something like 7 elements, but the first greedy choice can cover 8, so you pick that, then the next one covers 4, the next one covers 2, and so on. Right? But the way these proofs work is by charging arguments. So when you pick a big set that covers 8 elements, in unweighted set cover, I have to somehow pay $1 for buying the set. So we simply charge each of those elements 1 over 8. It's sort of the bill that it gets for the cost of the set. And then to analyze this, you look at the optimum solution and see what the charge is that any set of op might accumulate. And the reason this is important is that it will place a role in the problem I'm going to present to you. Right? So set cover and dominating set are fundamentally equivalent. So in dominating set, you want to find a subset of vertices in the graph that finds the dominating set, which means that every node in the graph is either in the set or has a neighbor in the set. And again, you get this very simple log D approximation using the greedy set cover algorithm. This was one of the classical NP-hard problems proven by Karp. And at least when I was a student, I tried quite a bit to improve this log D bound. And then this beautiful paper by Uri Feige appeared that showed that you cannot improve, not only can you not improve the log D, but you cannot improve the constant in terms of log D. So 1 minus epsilon times log d is the hardness of this problem. Okay. So now what happens about connected dominating set? So that adds a new twist about connectivity. And so this is again, like I said, a very old piece of work published in ESA 96, which Sugipta Guha, and then won a Test of Time award 20 years later. And one of the reasons, there's nothing really deep in the paper. It's just some clever combination of greedy algorithms. I guess in the mid-90s, greedy algorithms, I would say fundamentally we didn't really understand the power of greedy algorithms. So they were applied a few limited settings, and now in hindsight you can say, well, they are very, very powerful. So in this CDS problem, the only difference is that the solution itself should induce a connected network. So for example, the previous graph I showed you where the vertices A and B form a dominating set, but they don't induce a connected graph because there is no edge. So then I have to add a new vertex to induce a connected network. So in the CDS problem, we're trying to find like a small tree, so to speak, which also forms a dominating set and induces a connected graph. Okay. So feel free to interrupt and ask any questions. Okay. Now the reason this problem became so hard is that it has many, many applications. So right around the time our paper came out, there was a whole community of wireless ad hoc networks, and they were trying to build like a backbone routing system within this wireless ad hoc network where these wireless devices are talking to each other locally. And this network, the CDS, was going to be used as a routing framework. I actually met a UMD alum who worked in a company, and he was surprisingly very familiar. He was an undergrad at Maryland, maybe he did his master's. And he was surprisingly familiar with this particular paper, and he was asking some questions about it. And I was like, how do you know this paper so well? I mean, he wasn't even a theory student, he was a system student. And he said actually when he worked for a company called Rockwell, he implemented our algorithm in the company, and they were selling the stuff to some fighter aircraft that were going to use this to communicate. So I was like blown away. I had no idea that this algorithm made it in some secret project in the military. And then Du and Wan published an entire book on CDS recently as well, which lists out applications as well as like what happens if you have special properties in the graph using geometry or planar graphs. Our work was on general graphs. Okay, so algorithm 0, the first time you come across a problem that you think about is just find a dominating set. We have good algorithms for that. And now you basically have a sanity problem. You have a bunch of nodes that you want to connect. So just solve a sanity problem, and so you can then prove that you get a bound of something like CS, where CS is the standard constant, multiplied by roughly 1 plus log d. Okay? So just by using like 2 libraries, you're done, right? So you have this. So the annoying thing is like, do we really need that constant C sub s, right? So the standard tree problem is solving a much more powerful problem because it's saying given any subset of vertices in the graph, how do I find the smallest tree to connect them? And so here, of course, now there's some nice properties because it's not any subset, it's a dominating set. And the standard constant keeps getting better. So when we first wrote this paper, it was something like 11 over 6. I don't know what the best bound is, but it's, I believe, now 1.4 something maybe. But still, there's a penalty that you have to pay there. And then people also worked on the problem where if the terminal nodes that you're trying to connect themselves form a dominating set, can you utilize that property in designing a better standard approximation? And the answer is yes. So there's a paper that I think shows something like a 4/3 bound for that as well. Okay. So what was the main result in our 30-year-old paper? So first we gave a very simple local algorithm that I'll describe. And the approximation guarantee of that was 2 log d. And then we showed how to get rid of the 2 by giving a centralized greedy algorithm which gives log d plus 2. So again, you might be able to improve this guarantee slightly. And I think there were lots of pieces of work improving it to log d plus 1 point something. So you can improve that slightly. But fundamentally, at least you don't pay a penalty of some constant multiplying the log d term, right? Because in set cover, the constant is 1. And as Feige showed, you can't improve the 1. So yeah, if you like using order notation for approximation guarantees, I will forgive you, but I don't like it. Because then if you use the order notation, you got no improvement, right? So, but this is an approximation guarantee. So when the paper is improving 2 to 1.997, I think it's worth at least not using order notation for this.
Sorry, what is D?
D is the maximum degree of a node.
Okay.
So in set cover, it's the largest set size. So here, the sets you can think of as a vertex and its neighbors. So that's where the D is coming from. Yeah. Okay. So what is the basic idea behind the algorithm, right? So the basic idea is very, very simple. Initially, imagine that all the nodes are sort of undominated and not chosen, so they're all colored white. And we can start from any single node and simply color it black and color its neighbors gray. So gray node means it's already dominated, black nodes mean you've paid for it, and a white node is not dominated yet. And we simply grow this solution, let's say one node at a time. So you have a black node with gray neighbors. Among the gray neighbors, you can sort of pick one of these neighbors that will give you the maximum benefit, right? So again, by computing the number of white neighbors it has and so on. And so you just start anywhere in the graph and just keep growing your solution until in the end, every node is either black or gray. And the number of black nodes you have is your cost, okay? It's a very, very simple algorithm that actually does okay in practice. People have implemented that. And so this is just a little animation showing you that you pick these black nodes, the neighbors get colored gray. So basically you're growing this tree, and at all points of time, the choices that you're making are picking one gray neighbor and coloring it black, and then the number of white neighbors it has is sort of the value or utility it provides, right? And so, and to make matters worse, my laptop died a few hours back. So thanks Rajni for her laptop, and so the slides that I made last night, you're not going to get to see because they're only on the laptop. Okay, but these are slides from a different talk that I had given, so I quickly added some stuff this morning. Okay, so what about this simple algorithm? It turns out it may do poorly, and you have to change the algorithm slightly. So it does poorly if you have no look ahead. So if you look at this simple graph that I have, what is the optimum connected dominating set in this graph? So you pick the top node and you sort of cover the top layer. And if you pick the bottom node, you color the bottom layer, and then you just pick one path and connect them. So the standard tree algorithm, the old algorithm, would do really well here. It finds a dominating set and then connects it, right? But this local algorithm can run into trouble because all these gray nodes look the same. They all have only one white neighbor. And moreover, even after you pick one of them and color this one gray, all the gray nodes still have one white neighbor each. So you might just make a mistake and pick this one, and then that one, and that one, and that one, right? So even though opt is very, very small, like 4, you may end up with a solution with something like D nodes. Okay. So how are we going to fix this problem? So we fix the problem by simply doing a look ahead. So at every point of time, we have some current tree that we've already grown. This frontier has these gray nodes. And rather than just focusing our attention on the gray nodes, we can mentally think, okay, so if I choose one of these gray nodes, I will get some benefit. And then the state of the graph will change. One new node will be black, a bunch of new nodes will be gray. So I can do a look ahead and say, what will I get in the next step, right? So now we want to run the entire algorithm from the beginning, where we are doing this look ahead and evaluating the benefit of a pair of nodes at every step. And that immediately solves this problem, because after I've chosen this node as black and this one as gray, while all these gray nodes have a yield of 1, they only have one white neighbor, this one, if it doesn't look ahead, will realize that at the next step, it can gain a lot. So that's what's going to separate these two choices. Okay, so we want to select the best pair. So you're paying for the best pair. And, okay, so this is the animation. And so we can prove that this gives you a bound of something like 2 times log d plus 1. Yes?
I don't know if I confuse myself, but like if you continue this pattern, like you have like a chain of length 3, why would this not get confused and still not find the best?
That's a brilliant question. Is the question clear? So he said that in this example, like I can mess up your look ahead by just adding one more node. The problem with that is the cost of opt shoots up, because now you have these multiple paths and then 3. So opt is not 4 anymore.
Right.
Yeah. So you're just going through the mental thought process we all went through 30 years ago, which is exactly that, the insight that extending it doesn't work, right? But of course, so it's a good question. So why is this look ahead too useful, and then 3, 4 is not that much more useful? So I have this beautiful slide that I made last night, which I can't share with you now. But I tried to now write in words. And as you know, a picture is worth 1,000 words, and I'm not using 1,000 words. So it's not doing as good a job. But, so here's the insight. Maybe I'll use the board and just show you one picture. So what's happening is that you have some optimum dominating set, which is sort of very high degree nodes which are sort of intuitively connected and all that, right? So what's happening is that we are making greedy choices by picking some other nodes, and then when we make a greedy choice, I charge all of the neighbors that I cover, and that depends on my degree d, right? And normally in the set covering proof, we sort of say, well, if this node had very high degree, say capital delta, then this was a valid choice, and so the charges to its elements has to be very low. But that's sort of not happening because we are growing this solution locally. We can only charge like d things, right? We haven't even encountered that node yet, right? But the point is that it's the nodes that it covers may all get a charge of 1, like exactly that happens in the prior example. These nodes are all repeatedly getting a charge of 1. So this is a solution of node of opt, very high degree, and all of its nodes are getting charged, and we sort of want to avoid that. So if each of these nodes is getting charged, they must belong to some optimum solution, and if that is a good solution, then the look ahead will give you that choice. So that's where the intuition behind the look ahead is. So it's just look ahead of 1 is sufficient. Because when I charge something, it is adjacent to something of opt who's unhappy that they're being repeatedly charged, so the look ahead will sort of fix that. And if you do the look ahead, then this becomes a viable choice, which means that choices that you're sort of making now have to be at least as good as that choice for you not to make it. That's the insight. Okay? So very simple insight, but the 2 is coming from the fact that we are paying for 2 nodes at every step. So we did not see a way to avoid the 2 in this algorithm. Okay. So now we began to think about centralized solutions for this problem, and there's a very simple centralized solution which simply says, now forget all this locality business, simply evaluate the goodness of a node by evaluating the number of white neighbors that it has. So if the node itself is white, that you get to cover 1 more, so that's counted as a white node, plus the number of adjacent black components. So even if a node is not white or doesn't have many white neighbors, if it has many black component neighbors adjacent to it, in the end you have to connect everything, so it's valuable to pay for that. So we simply sum these 2 terms, and that's the entire algorithm. So now things are happening all over the graph simultaneously. You're just greedily adding nodes based on the value function, which is number of white neighbors plus number of adjacent black components. And for this algorithm, we can prove the bound is log 2 plus 2. Okay, so now it's a centralized algorithm. It's not local anymore. And so that was the state of affairs till a decade ago. Now, of course, there were some people who were not happy with the algorithm because the running time is a little higher, because at every step I have to evaluate this look ahead. And so this paper from Microsoft Research came out which said, just pick 1 node and just pick a random neighbor of that node. And surprisingly that works, but it gives you the same approximation guarantee. So the approximation guarantee is still twice log d, but it's faster because you make sort of the best choice locally and then just pick a random neighbor of that person. And so we, in the 2016 paper, this is work with Sheng Yang, showed that rather than picking a random neighbor every time, there's a certain coin toss with probability p, and if the coin says heads, then you don't pick the extra node. If the coin says tails, you pick the extra node. And by picking p carefully, we can improve the approximation guarantee of that algorithm to something like log d plus square root log d. Okay? So it's still not desirable because of this extra square root term. And so the question that was facing us was, why can't we have a local algorithm that gives log d? Okay, so before I get to the result, I wanted to, I think there was a slide on this. Okay, this was the slide. So prior factor 2 log d analysis only actually compared to an optimum dominating set. So here we didn't use the fact that this optimum solution was even connected. And if you think about a simple graph that's a long line, the dominating set is something like n over 3, because each node will dominate itself and its 2 neighbors. But if you have to connect it, then the cost is very high. So connecting is expensive. But nowhere in that proof did we use the fact that the opt is connected, right? So that was bothering me for, I guess, 20 years. So when Sheng started his PhD, I said, okay, I have a problem for us to work on. And so we worked on this problem. And so we came up with a local algorithm without this problem. So here's the local algorithm. So this local algorithm is still working just in the same way as the local algorithm I showed you earlier. So I start off with any black node and basically growing it with this 2-hop look ahead and all that. But now the function that we use is bit strange. So it's still a local algorithm, but at every step we maximize FB, where FB is twice the number of white neighbors plus the number of black components minus 1, by only restricting to a 2-hop neighborhood. So the algorithm is still purely local, just use a slightly different measure and run it locally, and strangely the bound is log B. So I want to make 2 comments about this. So the proof is a little bit involved, right? So I'm not going to go with the proof. But first observation is that, well, this minus 1 looks kind of silly, right? Because if a node maximizes the function without the minus 1 or with the minus 1, it's the same. So that's true, the choice is the same. In the charging scheme, this minus 1 sort of becomes useful. So it's only because it just gives a clean connection between the proof and the algorithm that the minus 1 is there. Okay. So, how much time do I have left?
5 minutes.
Okay. So the one key point I wanted to say is that this new proof does not actually do local charging and utilizes the fact that the opt is connected. So the opt has to pay some price for connectivity, and that is utilized in this proof. Okay. Okay. So I also wanted to make a comment about another paper in SORA 2014, which this second result. So this is changing the problem slightly and saying rather than a full dominating set, I want to find a partial dominating set. So if I tell you here's a graph G with 10,000 vertices, but I only care to provide connectivity to 90% of the customers, for example, then how do I find the smallest CDS? And this problem is actually a little bit more involved because let's say I only wanted to provide service to 20% of the customers, right? That's just the input parameter to the algorithm. So now you sort of don't know, you can't just pick a node and start working there because you might be working in a very sparse region of the graph where every node is only covering one new neighbor. There may be some very dense portion somewhere else. So clearly local algorithm is out here. And so you kind of need to do something different. And again, there are a few papers that outline why this is an interesting problem, and then you can change it to say, I want to find a smallest dominating set, and rather than giving a threshold, I'll just give you a budget on how many nodes you can have in the CDS, and you want to dominate the largest number of nodes possible. So again, the approach that we have works for both of these problems and gives you, I think, reasonable solutions, but I think there is something more to do here. So for example, we do get order log D approximation here. There is a constant which I don't remember quite what it is, like 6 or 8. It's not huge, but it is there. So maybe one day there'll be a log D approximation for this problem, and this has something like 1 over 13 times 1 minus 1 over E. So just if I looked at budgeted dominating set, you'll get using max coverage that results 1 minus 1 over E. So we have to pay some penalty there. Okay. So I'm sort of done with the interesting things that I wanted to say. Oh, so there is maybe we have 1 minute? Yeah. So this sort of summarizes that entire SORA paper. And maybe the main thing to focus on is this second bullet, which is that we first define a value function. So value function is just take your graph. We're not even trying to find a CDS yet. We're just defining this value function. So if you imagine running greedy set cover and say, pick a node, how many neighbors will it dominate, and so on, just do this in an ad hoc manner, breaking ties any way you wish, and define a value function. So a value function is what is the utility of a node when it is added. Imagine that you had to build a full dominating set. Okay. Now, as you can see, this looks ad hoc because there could be 2 nodes, A and B, which share a lot of common neighbors. So if A gets chosen first, A has a huge value and B has no value. And if B is chosen first, B has a huge value and A has close to 0 value. But the algorithm says it doesn't matter. Just run your value function. It's completely ad hoc. It gives you a value function at the end. And then we just map it to a problem known as quota standard tree, which generalizes standard tree, but basically says each of these nodes has some quota or a budget. That is the value you get. And I want to build the cheapest tree giving a certain value. And we run this algorithm on that, and it does the problem. So the algorithm is just in one slide. The proofs are involved. Okay, so let me stop.
Thank you. Yeah, we have time for a quick question, or maybe 2. Samir again.
Thank you.